from NHC. And if you want to go ahead and start.
All right, good morning, everyone. Hopefully everyone was able to brave the traffic or get some good breakfast at the hotel this morning. My name is Philippe Pappen. I'm a hurricane specialist at NHC. And this was initially meant to be a tag team presentation between myself and Levi, but he's already kind of presented some of the model issues that he encountered this past season at JTWC yesterday. Although he may add a little bit of additional context to some of the scenarios that we encountered for the hurricane season in the Atlantic and East Pacific basins this year. And so I'm going to kind of start off with just a few kind of different categories of different issues that we encountered with some of our guidance this past year. We're going to break it down into genesis, intensity, track, and then also structural issues that we seem to have seen in some of the models that we found this year. And so starting off with genesis, let me see. Oh, actually, the laser pointer works. Perfect. So starting with some of the genesis issues that we encountered, really a lot of the guidance we have for making tropical cyclogenesis forecasts in our area of responsibility are almost exclusively reliant on global model data. And that's because we just don't have a lot of high resolution. The hurricane regional model guidance even isn't initialized until we have a feature that we can key on or an index that we typically designate for systems. And that's already after the system is already likely to become a tropical cyclone at some point, or at least we're able to key on a particular feature. So global model data is really our tool of note that we need to use for making genesis forecasts. And they kind of cover the gauntlet of different types of configurations and different parameterizations. And in particular, cumulus parameterization is pretty important for model guidance on the global model spectrum, where you have resolutions that are kind of in the gray zone of model physics. And because of that, this often contributes to the model bias for whether or not a particular global model is more prone to spinning up tropical cyclones and has too many false alarms relative to reality, or in the other side of the spectrum where it struggles to actually depict a nice, tight, coherent vortex that leads to TC genesis and has too little probability of detection. So here's just kind of a really rough kind of spectrum of our kind of suite of model guidance that we look at on a regular basis at the Hurricane Center. I show some of the deterministic models here on the bottom, the GFS, the Canadian, ECMWF, which actually just had an upgrade over the past 24 hours. So they're doing a little bit some updated model configuration for both its deterministic model, which is now really just a control member of the latest ensemble, which was also upgraded yesterday too. But based off what we saw in 2024, this was kind of a rough spectrum of what we encountered. The GFS still kind of struggles in producing too many false alarms. I do have a couple of cases that I'm going to kind of highlight that a little bit more, where oftentimes these biases are location dependent. So in the GFS's case, we see scenarios where the GFS often loves to spin up vorticity in the Western Caribbean Sea or even in the far eastern portion of the Pacific Basin. And at least in my opinion, it seems to be pretty heavily tied to its cumulus parameterization, where it produces a lot of bottom-heavy heating profiles that really helps to amplify incipient vorticity in the low levels. And it possibly might be linked to why it often loves to spin up vorticity a lot more so than some of our other global model guidance. The European is kind of on the opposite side of the spectrum, where it seems, especially in the medium range, when you get out to forecast lead times 5, 6, and 7, the ECMWF tends to struggle in depicting very tight, coherent vortices, where I'll show a couple of examples also in just a little bit, where it really loves to kind of keep a system very broad and loose and almost kind of just a large kind of broad gyre-like or monsoon depression-like configuration. And so this is actually a problem that happens a lot of times in the Western Pacific Basin too, where a system will start off as a very broad low-level circulation in the 5 to 6 day forecast. And then in reality, that actually ends up being a tropical cyclone that has a much tighter radius of maximum wind compared to what its model forecast was depicted. And I should mention the Canadian model. This is actually a lot different than what we even experienced maybe 5 or 6 years ago. It used to be a model that would habitually spin up too many tropical cyclones in the deep tropics. And really over the last few years, they've worked really hard to improve its model configuration. And actually its bias is actually maybe a little bit less than what the GFS is currently now, where it still has kind of leans a little bit more on the sort of too many false alarms side of the spectrum, but is roughly kind of in between the sort of more anemic ECMWF that has too little probability of detection, and then the GFS, which has too many false alarms. And then one thing I do want to emphasize here is that we also heavily use ensemble output, which tends to be more neutrally biased because you can look at a spectrum of model solutions based off the initial conditions, looking at a variety of different sort of perturbations to the initial conditions from these deterministic models. And so both the GEFS and ECEPS are kind of more in the middle side of the spectrum because you get these 30 or 50 individual solutions that you can provide sort of a probabilistic basis of tropical cyclogenesis forecasting. So moving on to some of the intensity issues that we encountered this year. Most of our model skill at the National Hurricane Center comes from hurricane regional model guidance and simple and corrected consensus aids that often blend all these forecasts together. So we're talking about IVCN, which is our simple sort of intensity consensus aid, HICA, which is the HFIP corrected consensus approach, which tends to account for some of the model biases with intensity forecasting, and then our suite of hurricane regional model guidance, so HWRF, HMON, COAMPS TC, and HAFS A and B. And focusing in on sort of the models that are being actively upgraded within NCEP, HAFS A and B are now using actually the same microphysics, the Thompson scheme in the North Atlantic Basin. And so that's a good thing in that the Thompson seems to be performing pretty well for tropical cyclone forecasting. But at the same time, because they're using the same microphysics, the diversity between HAFS A and B is actually reduced relative to what it was in the prior year in version 1 of HAFS. And so we actually see a lot of very similar solutions between HAFS A and HAFS B runs for the same exact cycle. And so overall, our seasonal intensity skill, as John presented yesterday for HAFS A and B, seems to still be lagging behind some of the older regional hurricane model guidance that isn't actively being developed. So talking about HWRF, and unfortunately, like HMON is actually our best performing hurricane regional model guidance for both the Atlantic and East Pacific basins this year. And so it stands to be, why are these hurricane regional models still outperforming HAFS A and B now that we're in year 2 of this new model framework? And then in particular with HAFS, we still see a lot of run-to-run variability, making it really difficult to be able to trust the given model solutions. And I'll show at least one example of that. The raw output also tends to be very noisy, especially in the very short-term forecast. And the real question I have is this actually a realistic depiction of the model initial conditions, or is this a rapid correction from the initial conditions that are being provided by the GFS at the very early on portion of the HAFS runs? Moving on to some of the sort of track issues that we encountered. Focusing on individual models, the GFS, when it forecasts very strong tropical cyclones, it tends to be too fast and too far right with its track forecast. And so a really recent good example of that was actually Rafael, which was consistently moving it very quickly to the northwest, further into the Gulf of Mexico, and then it basically gradually corrected towards a much slower solution that was ended up further to the left, more in the central Gulf of Mexico. On the other side of the spectrum, the ECMWF seems to be almost habitually too weak with tropical cyclone intensity. And then overall, for its track bias, tends to lead to it being too far to the south and west. And so it's kind of almost the opposite bias from what we typically experience from the GFS. And Beryl was actually a recent good example from this past year where it was consistently taking it either into the central Gulf of Mexico or even into Central America. And as we know, the system ended up sort of almost recurving into the Texas coastline and the western Gulf of Mexico. And then in cases where TC intensity is less influential on tropical cyclone track, it seems like the better synoptic skill in the ECMWF does actually lend to aiding in its track forecast. And so one recent example of that was actually also Rafael, where it seemed to capture a better, larger scale synoptic pattern that led to a more accurate track forecast once the system got into the Gulf of Mexico. And then finally, I kind of want to wrap up here, the last slide here, talking about structural issues. And I'm going to just focus here on the HAFS model initial conditions. And so we've seen this in several cases, even with very intense tropical cyclones, where the model tends to initialize with these sort of what appear to be unrealistic structures. So this is an example actually from Milton this past year when it was a Category 5 hurricane just north of the Yucatan Peninsula. You can see here in HAFS A and HAFS B, notice these splotches. This is the sea level pressure pattern here when it was basically a Category 5 hurricane. And notice these weird kind of patterns pretty close to the radius of maximum wind in the center of the storm. And the real question is, why are we getting these sort of artifacts showing up in sort of the initialization of the model? Is it related to the GFS data assimilation scheme that's impacting the HAFS initial conditions? So this might be a case where the data assimilation scheme of the GFS is being ported over to HAFS and may not necessarily be at the proper resolution to be able to capture some of the structural variability of the tropical cyclone. And in contrast, you can see HWRF seems to be a much more realistic sea level pressure kind of structure around Milton at this initial condition time. And so in other scenarios, when the GFS does develop tropical cyclones, it's often too fast to develop a symmetric vertically aligned vortex. And so these are cases where the storm rapidly intensifies basically in the global model in the short-term forecast and basically causes the system to be vertically upright and show a much more favorable environmental configuration for it to continue to rapidly intensify instead of a system staying a lot more sort of vertically incoherent and not able to take advantage of the favorable environmental conditions. And then there are issues with the internest of HAFS centering on spurious convection instead of the actual tropical cyclone vortex center. And this is actually a real big problem for weaker tropical cyclones or even systems that are being run in the invest stage where the internest will actually not key on the feature of interest that we're trying to track in the forecast, but actually starts keying on convection outside of that TC core. And if your internest isn't centered directly on the tropical cyclone, that could cause issues if you're not fully capturing its inner highest resolution right over the center. So I'll just wrap up. I see I have 5 minutes left. I'll show a few case studies kind of illustrating some of the sort of overall issues that we encountered this year in our area. So here's from Raphael, and let me see if I can just play this animation. This is a case where Genesis was really poorly depicted by the ECMWF. And this is another thing I kind of have noticed off and on over the last few years is that in the European analysis, and let me see if I can animate this one more time here, you see a lot of these spurious waves that appear in the model forecast over at least the first 5 to 6 days that seem to be unrealistic structures. So you see the sort of rapid propagation of features that are radiating outward from an area of initial convection in the model. And these are propagating at phase speeds that are way faster than what's actually likely to be occurring in reality. So these aren't actually squall lines, but seem to be almost like gravity wave type structures that are showing up in the model. And at least at this time, the model is really struggling to show any sort of intensification of the initial feature that led to the development of Hurricane Raphael. You can see here's actually the 7-day ECMWF forecast, which shows a lot of vorticity over the Western Caribbean, but no real coherent feature. In fact, not even a closed circulation. And if you compare that to what actually occurred in the analysis, this is 0Z on the 6th of November. This was actually when the storm was initialized as a hurricane. We had our first, we had a few recon missions that update the system to a hurricane at that time. And you can see, at least in the European analysis, now it's capturing this tight little vortex that's just to the west of Jamaica at this time. That stands to be, is it partially related to some of these issues with all the spurious sort of gravity wave-like activity in the model, basically causing it to struggle and helping to spin up some of these low-level vorticity features. Here's a sort of similar case, except now for the GFS for Oscar this past year. So this is a kind of a storm that plagued us in the late portion of October, where we were tracking it for a long time as a wave that came off the coast of Africa, and several times looked very close to becoming a tropical cyclone. But once the system got kind of to the north of Puerto Rico, it had lost any sort of semblance of a surface-based circulation, and a lot of the guidance actually dropped developing the system entirely, especially the GFS. And so you can see, look at this rapid correction in the GFS from basically a 1 to 2 day forecast, where it just basically all of a sudden realizes, oh, actually there's going to be a nice little tight vortex that forms here very close to the Bahamas. And in fact, when we started the system as a tropical storm, we flew a recon mission into it, and it turned out it was actually a very tiny hurricane. And so I just want to point out that the GFS is not always immune to the lack of Genesis detection. In this case, this is a situation where it struggled to detect the development of Oscar in this case. And then Milton was a similar example here, where both the ECMWF and the GFS shows this very broad low-level circulation of the Gulf of Mexico. And then in reality, there was actually a much tighter vorticity feature that developed in the Bay of Campeche here in the southwestern portion of the Gulf of Mexico that wasn't really being well depicted in the medium range forecast for both the EC and the GFS periods. And then you can see that basically led us to have to ramp up our probabilities very quickly for a system that ended up becoming a Category 5 hurricane in the Gulf of Mexico. Part of that might just be due to the fact that the system was just so small, but it does stand to reason why are the models not able to depict that when you go out 3, 4, 5 days in the forecast time frame. We have issues with false alarms like I discussed with the GFS. Here's an example from May this past year where the GFS was spinning up a tropical cyclone in the far eastern Pacific, which is its common bias. The ECMWF shows a much broader feature. And at least in this case, no genesis took place here in the far eastern Pacific. And then just focusing on intensity issues here, this is again Oscar. This is actually the first HAFS forecast that was initialized when the system was a tropical storm in our at least initial time at 12Z. And you can see the HAFS forecast initially showed an open wave only about 25 to 30 knots. So this isn't even a tropical cyclone in this 24-hour forecast. And then the next cycle right after that, basically you have this big swing in the opposite direction towards HAFS being far too strong from being far too weak the previous cycle. And here's just a verifying sort of SAR pass to show the structure of the system, where it was about a 70 to 75 knot hurricane at the time that it went from basically being an open wave to a Category 5 hurricane. So which of the model suites do you trust? It seems like it's going windshield wiping a little bit too strong from run to run. And then finally, kind of wrapping things up, track issues with Beryl. You can see here's the HAFS-B showing consistently too far south in the Gulf of Mexico or even over Central America. And this was actually a case where the HWF forecast was a little bit closer to the verifying track over its lifespan, especially here in the Western Gulf of Mexico. And then there's a couple of issues that we've also encountered between our interpolated trackers and raw chalk output. This is an example from Helene showing our interpolated trackers were a little bit too far to the west compared to the actual raw output that we are seeing from the GFS and ECMF. We're working with NRL right now to be able to see some of these tracker issues. So I'll end it here, and I'm out of time. Thanks for listening.
Thank you, Phil. In the interest of time, we will move on, but definitely we'll look for answers to these questions. Why? My name is Vijay. I'm the session chair here today. Next talk is by Jan Jang and Gus Alaka, talking about the issues from modeler's perspective.
Thanks, Vijay. Good morning, everyone. My name is Zhang Zhang from EMC. And today, Gus and myself are going to talk about the HAFS performance verifications, and we will basically we are focusing on the challenges in 2024 hurricane seasons. Next slide.
Yes. You can use the
Oh,
arrows on the
okay.
remote.
All right. So this is okay. Yeah. So here's the outline, and first I will talk just to give a brief talk about the performance of HAFS verifications in 2024, and then we will be focusing on the issues and the challenges with the HAFS model development, and followed by the plans and the future HAFS development. So this is like a busy slides basically showing the track and intensity forecast for 3 major basins, North Atlantic, East Pacific, and West Pacific. I will just summarize the performance. By the way, this is the later forecast model. Unlike the previous talk, is the NHC verification is always focused on the early model talk. So early model verifications. So basically, in the North Atlantic, the GFS track has the highest track forecast skills, followed by HMON, and then the HAFS-B and HAFS-A, and also HWF. And for the intensity forecast, actually, if you look at the later forecast, HWF is actually performed the better, is the best, and then followed by HMON, and also, I mean, HAFS-A and HAFS-B is kind of behind. And East Pacific basins, GFS, for the track forecast, GFS, HAFS-A and B had the highest forecast skills in the track forecast. And for the intensity forecast, HWF and HMON performed the best. And for the West Pacific, you can see GFS also have the best track forecast, followed by HAFS-A. Then GFS also have like highest intensity forecast skills after they fall. So another verification we normally do is the verification for the rapid intensification cycles, and we have 2 methods. One is the RI performance diagrams, and in the left side, and also the Frank DeMaria's method in the right. So basically, what this slide shows is that HAFS-B and HWF performs the better than HAFS A and HMON in the RI events. And HAFS B actually has a better probability of detection than the HWolf. And if you look at the right side for the RI cycles verifications, basically before day 3, all these four models are performed similar, and they diverged after day 4. So I just try to briefly mention several successful cases in 2024 hurricane seasons. Basically, I mean, Hurricane Helene and also Milton both HAFS models, HAFS configuration did pretty well in terms of both tracker and intensity forecast, especially for the RI forecast. You can see in the lower panels, actually HAFS A and B did pretty well compared to other legacy models, HWolf and HMON. But this is just cherry pick one case. And another thing I want to mention is like for the Milton cases, HAFS A captured like a secondary IO structure pretty well. I mean, the top is the wind speed comparison with HAFS A model output model filter with the observation TDR data and the reflectivity in the bottom. Basically, it's captured both the directed intensifications. The issue, I mean, it was a slightly larger storm size. So this is another case is comparing the model output precipitations. This is 3-day rainfall precipitation compare HAFS model output compare with the climatology calibrated precipitation analysis. You can see it captured both patterns and amount pretty well. So I will focus on the issues and the challenges we identified in the 2024 hurricane seasons. And one of the major issues we identified actually in the previous several talks mentioned that HAFS config both HAFS and B have initial imbalance issues compared to the HWolf HMON. You can see I circled it had the largest 6-hour intensity forecast error compared. I mean, it's just a jump a little bit in the error at 6 hours. So it indicated the model imbalance in the initial time, and the root cause we are still under investigations, and we are trying to mitigate these issues. Like right now, we are try to one of the features we did not include it, but included in the HWolf is the wave number filters. So we are trying to use wave number filter to try to mitigate issues, and also increment analysis updates in the data simulation. You can see actually the right side, you can see the fields compared to HAFS and HWolf. HWolf actually have a better initial model structure. And another issue we identify is the cycle-to-cycle intensity volatilities. And you can see that in the right side, it shows 2 consecutive cycles, the red one and the green one, and the bracket is the best track. You can see the red, the previous cycle, 6Z cycles predicted RI pretty well, and the next cycle is just dropped off. The intensity is just, there's no RI happen in the next cycles. And we look at this, if we look at the track forecast and compare the red track and the green track, you can see the green, I don't know if you can see clearly, the green as the second track forecast is like, it touched a tip of the U10 a little bit. That's caused the next cycle did not intensify. And we also look at the intensity, the hurricane ensemble forecast. You can see basically whenever when the track forecast have a little bit west, move a little bit west to touch the U10 tip, you will not have the rapid intensifications. So this is a kind of model model uncertainty issues. So another cycle to cycle volatility is the Hurricane Christie. You can see that it's lack of the intensity for consistency, and the previous cycle intensified, and the next cycle just spun down. And we do not find any causes of this. And some of the notable issues is showing in the right. The reflectivity patterns are kind of different between the two cycles. And another issue we identify is the vortex tracker issues. I mean, for the weaker storms, you can, this is just one example. So we are showing we have several such kind of things. You can look at the animations in the right side. You can see that somehow the internal track just did not follow the storm centers, and the moving net moved the wrong directions. And so basically the model lost the track of the storms. And for the ocean responses, I mean, we compare the model output with the sail drone, and basically all the models captured the SST pretty well, cooling rate pretty well. But if you look at the right side, comparing with the model output with the sail drone, you can see all the models have a color bias compared to the sail drones. And also another one is that if you compare the model salinity, you can see model have a lower salinity compared to the observations. And another issue is actually this issue was reported by JTWC last year, and we are working on it. You can see basically the issue is that this is just one case. For some initialization pressures, the HAFS has like a very deep storms compared to the HFIP and the bass track. You can see in the middle panel explain the issues. This is actually coming from the JTWC last year's presentations, and we continue working on it. And in the right side, the top right side, we mitigate these issues by use different composite storms and like different intensity methods, different vortex initialization method. You can see we continuously improved from HAFS version 2, and in the new versions we tested in the parallel versions and the latest version. We also use the same VI method to do like large sample size for West Pacific and East Pacific. We find that the new vortex initializations improved both intensity forecast. So this we consider these issues like mitigated or improved. So we have several challenges storms: Hurricane Barry, Oscar, and John, and the East Pacific. Do I have time or? I have 2 minutes. Okay, I just go quick. I'll say one of the issue is the track in Barry. I mean, it's already mentioned in the previous talk, and also for the Oscar. I mean, this is actually have the same issues like intensity issues, and basically it's Oscar is kind of very small storms, like tiny storms, and also for Hurricane John, it's not only HAFS model. All the regional models at the beginning missed the track forecast, both tracker forecast and also rapid intensifications. So this is my slide, last slides. So this is the plan for the future HAFS upgrade. And because of the GFS version 17 upgrades and also the JEDI development, we need time to. So basically for the 2024 upgrades, we will have minor no science upgrades, which is just compared because of due to the upstream RTOF upgrades. And for the 2026, we will have GFS V17 upstream upgrades impact. And also the next major upgrade will happen sometimes in 2026 or 2027. I mean, basically we were focusing on the JEDI transitions in the HAFS version 3. And like a basic DA features will include the MOM6 3D DIVA and also a simulated more data simulation. 3D DIVA will, you will hear more in this afternoon by Jing's talk, and more data simulation topics will talk by Xu tomorrow, and also we will implement some IRA and waves and increment filter method, and also for the vision for the next HAFS version 3, we will probably have for the HAFS version 2, we will continue to use the storm centric with a higher resolution, like 1 kilometer resolution, and HAFS B version 3 we will try to use multiple moving nests in the basin scale domains, and also we will, based on the 2024 real-time experiment, we will implement some of the model physics experiments. And finally, we will try to use three-way atmospheric wave and ocean model couplings. And finally, we will, I mean, that's the far future. We will use AI-based hurricane ensemble forecast systems. I will end here. Thank you.
Thank you, Zach. Well, we ran out of time, so we will reserve questions for later in the session. The next speaker will be Julian Hemming from UK Met Office. Julian.
Hi there. Can you hear me?
Yeah, we can hear you, and we're setting up your slides here. Give us a second.
You're going to run them from your end, are you? I'll just say thanks again for the opportunity to speak at the meeting. It's always good to catch up on all the developments that are going on.
Sorry, BJ, bear with us for a second.
Yeah, give us a second.
Hi.
Are we driving?
Are we ready to go?
Yeah, we are driving. I think we are driving here.
Okay, we're good.
Okay. Okay, an outline of what I plan to say. I'll do a bit of a covering the Met Office global model performance in 2024, and then I want to pick out a few of this year's hurricanes to make some comments on, some of which have already been touched upon in earlier talks, actually. And also make a mention of Pangu weather, which is a AI-based model which we've been doing some experimenting with. And then towards the end, I want to talk about the next Met Office model science upgrades and the longer plans for the Met Office model. So next slide, please. Okay, starting off with Met Office global model performance. I think I mentioned this in previous meetings. Back in 2022, the deterministic and ensemble models were coupled to the ocean and had some physics upgrades, which were an improvement for NWP scores, but did make storms much weaker. And actually, if you look at the plot on the top right, which is central pressure bias for tropical storms over recent years, those three dotted lines at the top of the last 3 years showing a weak bias for tropical storms. And that's something we're having to live with at the moment, having a weak bias for tropical cyclones, which we hope to address in future science upgrades, which I'll talk about later. Bottom right is a long sequence of track forecast errors. Again, I've done this for the whole Northern Hemisphere. And just to say that this current year, which is obviously the far right-hand side, some of the forecast lead times, actually the errors were the lowest we've ever had, but mostly they're on a par with the last few years. So track forecast errors kind of riding along at much the same in the last few years. That's for the Northern Hemisphere. For Atlantic, which I'm not showing any plots for, this year has been a little bit lower than last year, but close to the kind of values for the last 3 or 4 seasons. So we can move on to the next one. So picking out a few individual hurricanes to talk about first, Hurricane Beryl. top right, I'll be showing some of these plots, which are kind of multi-model ensembles. So you see the track and the intensity for the various deterministic and ensemble models, the ECMWF, GFS, and the MOGREPS, which is the Met Office model. As I think we're all aware that the rapid intensification of Beryl was not that well handled. It was better in the GFS and ECMWF than MOGREPS, as you can see from the far top right, where you can see the various intensity predictions from this one particular case I've pulled out. If you go down to the bottom, as has already been spoken about in particularly in Philippe's talk earlier, there was, for some of the models, particularly the MOGREPS, which is the yellow tracks you see there, and the blue is ECMWF. There was a left of track bias for Hurricane Beryl as it moved into the Gulf. But then on the far right, bottom right hand side, as we got closer to the event after moving into the Gulf, the track forecasts picked out landfall eventually in the right place. Next slide. I want to look at Hurricane Helene now, and what these plots are showing is they're all the forecasts verifying at one particular time. I've picked the time which is just before landfall. So on the left, you see a sequence of forecasts from the Met Office global model. On the right, I'm comparing them in this instance with the ECMWF, just to show how well landfall was captured. And you can see from this sequence, which starts the longest lead times at the top left, shortest lead times bottom right in each plot, that in the Met Office global model, that the landfall timing of Helene was picked out quite well up to 4 days in advance, but not beyond that. It was a bit slow beyond that, held Helene back out in the Gulf. ECMWF model, just for comparison on the right, was a bit better in terms of it picked out landfall timing up to 5 days ahead. But again, beyond that was a bit too slow. Both models were too weak well in advance, and gradually got closer to the right intensity as we got closer to the event. If we go on to the next slide, which looks at another aspect of Hurricane Helene. First, we're looking at the actual location of landfall. The location was very well picked out by all the models, and the plots you see here are just for the MOGREPS, which is the Met Office ensemble, and the deterministic is on there as well. Although the speed of movement was had some errors, the location of landfall was well predicted, as was the slowdown and the turn to the left once Helene got inland. And what I wanted to pick out, particularly in these plots, at the bottom left, we show an example of the predictions from the Met Office global model of rainfall, because obviously that was the significant event with Helene, and showing that for the full, this particular forecast for the full 7 days of the forecast, so that will include the kind of predecessor rainfall event ahead of the hurricane itself. And you can see in several runs, the model was able to pick out values in that area circled over western kind of North Carolina area, where we saw the heaviest rain, up to about 550 millimeters of rain in the global model. So in terms of rainfall, the global models were able to capture that event quite well, and particularly how it phased in with Hurricane Helene and how it slowed down as it moved inland. Next slide, please. I'm picking on Hurricane Kirk here because this had some interest in the UK, because obviously Kirk stayed well away from the US, but made a recurvature. And you see top right there, one of the GFS forecasts was predicting a track right across the UK, presumably as an extratropical system. But I've picked out here something which I'm just throwing out there as of interest. So I don't know whether anyone might want to look into it further. And that there was an interesting structural prediction from the GFS model for quite a few runs. And the kind of bottom left chart shows the phase space diagram from the Met Office global model as Kirk was recurving and making extratropical transition. And you can see it did the traditional type transition from symmetric warm core through asymmetric warm core to asymmetric cold core as it moved towards Western Europe. But for several runs, the GFS was doing something very peculiar, which our forecasters came to me to find out what I thought was going on. And I wasn't entirely sure, because GFS seemed to be predicting, as the recurvature was happening, yes, it was moving to asymmetric warm core, but then that process reversed, and for several ones, it was moving back towards a symmetric warm core as it was reaching UK and Western Europe. Now, the question mark, what's the reasons for this? I've speculated was it predicting some kind of warm seclusion event in what was an extratropical system, so thus giving it some kind of warm core? I don't know, but eventually, as we moved towards the landfall time, the GFS did come into line with a more expected transition through to asymmetric cold core. And of course, in the event, Kirk came ashore a lot further south than early predictions over kind of southern France. So it didn't actually have any direct impact on the UK after all, even though we were concerned at the longer range that it might do. But I just throw that out there as something of interest, what was going on with the GFS during this time. Next slide, please. I'll mention Hurricane Oscar, which has already been spoken about a bit. I've again picked out doing this kind of fixed verifying time plots on the left for the what is not actually the operational Met Office global model, the new configuration, which is slightly better for intensity, and on the right ECMWF. And I've picked out a time when Oscar was a small 75 knot hurricane near Cuba. And I think Oscar has been characterized as a bust for the global models because of the very tiny size of Oscar compared to the relatively coarse resolution of the global models. But actually, if you have a look through some of the global forecast sequences, that's not quite the whole story, because there are some forecasts from earlier lead times which did actually spin up quite a small, tight chord system, maybe not hurricane strength, but certainly something which is closer to what we saw closer to the event, if you like. And if you look at the kind of red boxed areas, so on the left, the Met Office model from about 5 and 6 days ahead was actually spinning up something which looked fairly good as it turned out, but then it lost it in the later forecasts. And again, on the right hand side, you see with the ECMWF forecast, it was able to predict something even further out, say 7 to 8 days ahead. But then as time went on, it lost it. So it seems that the global models did have some capability to be able to predict a really tight chord system like Oscar. But although they had it in the longer ranges, they then lost it closer to the event. And I'm not entirely sure of the reason for that, but that's something which may be worthy of further investigation. Can we move on to the next slide, please? I want to talk a bit about the AI machine learning models now. We're developing various of these types of models at the Met Office experimentally at the moment. But one we've looked at in a bit more detail is Pangu weather, which is an AI model which we ran actually in near real time here from January to June this year. So unfortunately, it didn't encompass the hurricane season, but it encompassed quite a lot of good tropical cyclone activity, primarily in the southern hemisphere. And I've evaluated some of the performance of that against the conventional NWP model, and generally found that the Pangu weather was much better for track forecasting, 7% lower track forecast errors. I've got an example here down here, bottom left, of Cyclone Iali, which was an unusual storm in the Southwest Indian Ocean, which had a very strong right of track bias in our global model. But Pangu weather, it reduced that bias considerably. That's just an example of the kind of improvements in track forecast we saw. But intensity, it was not good at all. On the bottom right, you see the pressure bias. And obviously, as I've already said, the Met Office global model has a weak bias, and the Pangu weather, which is the green line there, has an even greater weak bias. And I think this kind of typifies what I think we've seen with a lot of AI models, which I've read about, in that the track forecasts do seem to be better, but intensity not necessarily so, particularly if you're training your model on relatively low resolution data like ERA5, which I think a lot of models are. So that's something to certainly give us some food for thought. If we go into the next slide, although I said that it wasn't running during the hurricane season, we did manage to do an ad hoc run of Pangu weather covering Hurricane Milton. And again, I did find that it was better, particularly for the location and timing of landfall in Pangu weather, than comparing it to the Met Office global model. An example here, I picked out the verifying analysis from when Milton was just making landfall over Florida. And so 3.5 days ahead, the Met Office global model was too fast. It had already taken Milton across Florida out into the Atlantic, whereas Pangu weather was much better, held it back, and had the location of landfall fairly good. And that was typical of what Pangu weather was doing for that. But as you see from the intensity predictions, it was far, far too weak. And that plot there shows a succession of forecasts of central pressure. The blue line is the observed, and obviously both models were poor, even though they were initialized relatively well and lost the intensity very, very quickly. So Pangu weather didn't handle the intensity at all, and it was worse than the global model. If you can move on to the next slide, I'm coming towards the end now. I'll just talk about next global model changes. I think I might have mentioned this one before because unfortunately it's getting delayed, or it has been delayed over the last year or so. The next global model configuration, which we terming GC5, includes further changes to convection, which produces stronger tropical cyclones, and it improves track forecasts and ensemble spread. So we're running it in near real time, kind of internally for internal assessment. And these are some of the latest results on that. So bottom left is the track forecast, which show a reduction of about 4% in the track forecast errors with this new configuration of the model. And on the bottom right, the pressure bias, there is an improvement. The pressure bias is reduced, but there is still a weak bias even after this this model improvement, this model configuration is implemented. Unfortunately, because of delays in migration to our new supercomputer, which has to come first, this next major science upgrade keeps getting pushed back, and it's unlikely to be before late next year now, because we need to get onto the new supercomputer now, which now looks like it won't be until well, it'll be sometime in the first half of next year. But that's something we're looking to in the future. If you go to the final slide, I can look a bit further into the future with long-term plans for Met Office modelling. Top point there is what I've just spoken about, GC5 science configuration. At that time, we're also going to extend the MOGREX-G ensemble from 7 days up to 10 days and move to a DOPA, which is a JEDI-based observation processing. Then if we move further into 2026, we intend to introduce what we're calling a Trailblazer 5-kilometer resolution global model. So it's a kind of reconfigured each run from the operational 10-kilometer global model, but to just give something a bit different, bit higher resolution. And in some trials, it's shown that it does better for tropical cyclone intensity than the 10-kilometer operational global model. But the 10-kilometer model will still be the main global model, which will be used externally, kind of passed out for external use at that time. But by late 2026, we plan to increase the ensemble resolution once we've made full use of the new capacity on the new supercomputer, increase the ensemble resolution to match the deterministic model. So we'll be in the same position that ECMWF are now, in which case the deterministic and the control ensemble are the same. And so you effectively have one of the same there rather than two separate predictions. And then looking a lot further, well, through to 2027, 28, there is actually a complete rewrite of our global modeling system going on at the moment, and that's called the ELFRIC model, and it will replace the current global model in that kind of time frame. And it's, as I say, a complete rewrite, dynamical core, parameterizations, moving to away from a Lapland grid to a cubic sphere grid. And we'll also include JADA, which is a JEDI-based data assimilation system. That model is already under development and some initial tests, and it does show generally slower error growth for both tropical cyclone track and intensity for the cases, or for the periods I've looked at so far. It's slower error growth than the GC5 model, which of course is the one which isn't yet operational and itself is better than the current global model. So in the longer term, it looks like there's scope for certainly some improvement in tropical cyclone predictions from Met Office systems in the longer term, once we're able to get some of these science and modeling upgrades into operations at some point into the future on the kind of timescales that you see here. So I think that just about covers all I wanted to say. Thanks for listening, and that's it. Thank you.
Thank you, Julian. We will keep moving on. Please wait until the last speaker so that we can use the Q&A session for discussion. The next speaker will be Linus Magnuson from ECMWF. Linus, can you hear us?
Yes, and can you hear me?
Yep. And
Great.
we can drive these slides for you.
Yep. So thank you very much. So I will give an update from Eastern WF and also discuss a couple of cases. So this is results I put together with my colleague Fernando Partes and Mikael Meyer-Gaba. So what was already mentioned in the session, we had a upgrade of our forecasting system yesterday. So now we're running model cycle 4901. So the different type of forecast we're running is the 9-kilometer ensemble system in for the medium range. And then we have an extended range ensemble system with 101 members going out to 46 days. Then we have a seasonal forecast. Then I will also in this talk briefly mention 2 experimental forecasts. So we have our machine learning based AIFS, which runs with a 1/4 degree resolution out 15 days. Plus we also run the other machine learning models in real time. Then we also have the Destination Earth initiative, where we for internal use only run daily 4.4 kilometer runs out to day 5, which are useful to look at in the context of tropical cyclone. Next slide, please. So with this cycle 4901 that was implemented yesterday, there is, as usual, a very large package of changes. But what's worth mentioning for the tropical cyclones is the change from the SPPT to the SPP model uncertainty scheme. So the SPP is a perturbed parameter scheme instead of the perturbed tendency scheme we had before. Then for the ensemble data simulation, which is used for the error covariances in the data simulation, but also the initial perturbations for the ensemble, we increased the resolution from 18 to 9 kilometer. And for the model, there were a lot of changes. But for example, we updated the ocean wave model to match the resolution of the atmosphere, and also some changes related to the heat flux. And then it was a lot of other changes. Next. So if you look at the ensemble verification of the pre-operational 4901, which we see in red, compared to the 4801 cycle in blue, we see the ensemble spread in solid and the ensemble mean error in solid and ensemble spread in dashed for position to the left and intensity to the right. So for position, we can note that we get a little bit more spread out from the new cycle. And if we look at the intensity, we can see that we got quite a lot of extra ensemble spread with 4901, and that's partly due to the higher resolution in the ensemble data simulation, given stronger cyclones initially, and also result of the SPP model uncertainty scheme. Next slide. So the effect of this increased spread in intensity, we can see here for one of the forecasts for tropical cyclone Beryl before it hit the Caribbean islands. So to the left, you see the 4801 forecast, each ensemble member in gray, then the high resolution and control forecast in red and blue. And then you can see the 4.4 kilometer destination Earth forecast in purple. So you can see that the whole ensemble in 4801 underestimated the intensification of a barrel at this stage, while it was much better captured when we go to 4.4 kilometer resolution in the destination Earth run. And if you are interested in more statistical evaluation of this resolution, you can look at the Sharan Mayumdar's paper in Monthly Weather Review from last year. If we then go to the 4901 ensemble to the right, you can see that we get much more ensemble spread, both at the step 0 where all the gray lines start, but then also you see that several members actually capturing the rapid intensification. And that's at least partly due to the perturbed parameter scheme, where, for example, the different parameters in the convection scheme are perturbed. So that it kind of opens up to in the future dive further into the model and see where in the parameter space we get these rapid intensifications. So next slide. So another change we see with the 4901 ensemble is just the number of cyclones that we see in longer ranges. So here we look at the count of the cyclones day 5 to 15 for different wind thresholds on the x-axis, and on the y-axis is the average number of cyclone per time instance. So you see what's coming out from the IB tracks in black, and then with 4901 in blue and 4801 in red. So you can see that we get more cyclones in the new cycle. So it would be interesting to see how that affect the conclusion that Philippe presented previous about lack of cyclonic feature in the ECMWF ensemble. We have not run any probability of detection yet to see that we actually predict that these extra cyclonic features actually increase the skill. So next slide. So coming to my choice of difficult case, and I actually picked up the tropical cyclone Debbie, and looking at the difficulties pre-genesis. So on the top here you see 4801 plus the AIFS machine learning model in green for a forecast from the 31st of July, 1st of August, and 2nd of August. And we can see that the forecast from end of July predicted a curvature before or east of Florida, where when we get to 1st of August, that first of all got a much weaker signal out from the model, but then it started to converge into more Gulf of Mexico system, which it converged to on the 2nd of August. And one can note here that also the machine learning model struggled, at least in a deterministic sense, with this case. For the 4901, we see a larger ensemble spread in end of July, which is in line with the statistics we saw before. So it already on the 31st of July had a few ensemble members having the cyclone in Gulf of Mexico. But then it also struggled on the 1st of August before it converged on the 2nd of August. Next slide. So coming into the verification of the IFS versus AIFS for this season, you can see the mean position error to the bottom left. And our impression, we haven't looked into it in detail, but it seems like the gap between IFS and AIFS is less for this year compared to last year, at least up to day 3. Then we see that IFS struggles more going into day 4, day 5, which is consistent with what we saw from NAC yesterday. Similar to all the other machine learning models, we see that we get weaker cyclones out from AIFS. Next slide. And this slide shows the same, but for the North Atlantic. I forgot to say that the previous slide was for the global sample. And here we see a little bit of a more advantage for the AIFS machine learning model in terms of tracks. Next. So that brings me to my summary. So with the implementation of 4901, we see more initial spread for tropical cyclone intensity, and we get more active tropical cyclone intensity forecast. So we get more spread, which means we get more intense systems, but we also get more very weak systems in 4901, mainly due to the perturbed parameter scheme in the ensemble. And we see more tropical cyclone genesis. Then I showed example of the high resolution experimentation we do within the destination Earth. Then we run the real-time experimental AIFS model and also other model. And we have started during the summer to run AIFS ensemble, but it runs with 1 degree resolution, so we haven't put priority to make tropical cyclone products, but it's in the pipe. And one opportunity we have on exploring how to combine the machine learning framework and this high resolution in destination Earth is in a EU-US initiative, AI for Public Good, where we hope to collaborate between ECMWF and NOAA on machine learning and high resolution modeling. I'll stop there.
Yeah, thank you, Linus. We will take questions after all the speakers are done. The next talk will be by myself from EMC. This is a perspective from EMC in terms of the real-time performance and where we are heading in the future. A lot of thanks to the Hurricane team and other project teams at EMC who have provided this input. Next slide. Got it?
Okay, no.
No. All right, so just an outline for this talk. We'll be talking about the performance of global deterministic and ensemble systems thus far, the UFS R2O project, which is helping us develop the next generation global models, potentially for implementation in FY26. We also have some early results from the AI ML-based data-driven models using GraphCast and GDAS that I will potentially touch on. Yeah, you can just do the next. All right, so we'll talk about the track and intensity verification from global deterministic first. These are for the first 16 storms in the Atlantic, 13 storms in the Eastern Pacific, and 23 in the Western Pacific through end of October. Thanks to Jai for providing these results. They are available online for people who want to explore further. Next slide. In the deterministic Atlantic, ECMWF certainly has better tracks through 72 hours, GFS leading the pack at the longer lead times, particularly beyond 96 hours. And intensity errors, as mentioned yesterday, GFS has the lowest intensity errors and competing with the regional models now, outperforming all other global models in terms of maximum intensity at 10-meter winds. Next slide. Eastern Pacific, same story. ECMWF has a little bit better skill till 48 hours. GFS better beyond 48 hours, and also lowest intensity errors from GFS compared to other global models. Next slide. Western Pacific is slightly different. EC and GFS have pretty much tied for track forecasts. GFS, again, lowest intensity errors through 144 hours. The sample size is not that big beyond, so not worried about that. Moving on to the ensemble forecasts, we continuously evaluate the global ensemble systems, both from UK Met Office, CMC, ECMWF, and GFS. Next slide. And these are the results. All ensembles have, ensemble means have similar track through 120 hours. CMC stood out, particularly at longer lead times for the Atlantic tracks. Just like the GFS, the global ensemble forecast system has the lowest intensity errors at all lead times. Next one will show the results for the Eastern Pacific. ECMWF ensembles have better tracks through 96 than tied with the global ensemble forecast system from NCEP. GEPS continues to show outperforming intensity errors at all lead times in the Eastern Pacific. For the Western Pacific, next one. The track forecast, ECMWF still performs better through 120 hours, and GEPS significantly improved intensity forecasts compared to any other ensemble system through 144 hours. We also looked at the next one. We also looked at the TC genesis. This was talked about by Phil in the morning and has been investigated as well from our model development point of view. The TC genesis, you can see GFS is too happy to produce more false alarms. And compared to the ECMWF or Canadian models, GFS has a tendency to produce more false alarms than the actual probability of detection. Eastern Pacific, not so much, but definitely the density of genesis locations is higher in GFS compared to European Center and CMC. The next one is the Western Pacific. These are the verifications for the TC genesis, both for the North Atlantic and Eastern Pacific. Not much skill, and they all are pretty much clustered. ECMWF definitely has an edge over the Canadian and sub-ensembles, both for Atlantic and Eastern Pacific. This is something that we will continue looking into. Next slide. These are the Western Pacific genesis. Again, you can see more density of genesis locations in the Western Pacific compared to the other EC or CMC ensembles. And the verification also suggests in the next slide, ECMWF definitely has an edge over both GFS and CMC. Next slide. So where are we going from here? I'm not going to delve on all other problem storms that were discussed so far, but we will talk on about how we are making future advancements. And I provided these updates last year too. We are making steady and significant progress in developing a fully coupled net system for medium range and subseasonal predictions. This is the schematic of UFS with all 6 components. The seasonal forecast system also is being developed in the same framework. We're targeting FY 26 for implementing GFS version 17 and GEPS v13, and potentially FY 27 or 28 for SFS, the next one. As part of the development, we showed the results from HR1 and HR2 last year. This year, we have completed more runs from HR3 and HR4. These are high-resolution prototypes testing various physics advancements and higher resolution, 9-kilometer, C1152. We have 2 more potentially prototypes before we can freeze the final science configuration and start the retrospective testing. Next one. Some results, I'm not showing any tropical cyclones here, but definitely the scorecards comparing HR4 with operational GFS or the previous versions of HR configurations. You can see huge green in terms of both anomaly correlations and RMS errors compared to ERA 5. And these are definitely showing a lot of promise in terms of improving the GFS forecast skill rather dramatically. Next one. This is the RMS errors. Again, you can see more green than red relative to ERA 5. Even in the tropics, we have improvements, except for some low-level biases in the tropical heights. These probably will be corrected once we have the data assimilation cycling going on. Next slide. We can skip this one. Next one. So these are the cycling results of very preliminary coupled data assimilation, weakly coupled. The marine components are using JEDI and atmosphere is still using GSI. Evaluation is going on, but the early results are pretty promising. This is anomaly correlation on the left and looking at the SST from the coupled model. And they are showing encouraging results, and we continue making progress with these cycled experiments. Next slide. GAPS V13, we are almost at the final stretch. We have frozen the configuration. This is undergoing now the extensive 30-year reforecast production. The model is now coupled to ocean waves and ice. We will not have aerosols coupled. This decision was taken not to include them due to several issues that required more development. But now we have started the production of 30-year reforecast, and very soon, probably in the next 6 months, we will be finishing them and getting it ready for implementation in 26. Next slide. These are the prototypes that we have done to test and validate various innovations. Each prototype takes about 9 months. So we have done up to EP6, and all the results confirm that the model has shown significant improvement. Next slide. In terms of MJO, for instance, we have gained almost 5 days of skill from the coupled model and the GEFS. And that now is comparable or close to what the other operational centers are doing in the world, including European Center. Next. MJO propagation, this is one that was lagging in our current operational system, and we have made significant progress in improving MJO propagation in the latest prototype for the ensembles. That gives confidence that the tropical cyclones also will be improved on the longer timescales. Next one. These are the scorecards, again, comparing EP6 to the previous prototype, all showing positive improvements, confirming that the changes that we put in are going to yield better results in real time as well. Next slide. Very quickly on AI/ML-based weather emulator and bias correction model development. This is the new project that EMC has undertaken. A few people here started working on using GraphCast and using NCEP analysis instead of ERA 5 to produce data-driven models. Next slide. This is experimental real-time GraphCast using GDAS initial conditions. The resolution is quarter degree, and there are about 13 levels and a few variables, both surface and upper air. And the schematic shows how this GraphCast is being rolled out in our experimental setup. And the next slide will show a few results. I mean, this is, again, the training part of it, using the GDAS data, tuning the coefficients from the GraphCast, and train them using recent data from global data assimilation system. The next one will show the results. These are real-time results from the experimental as well as the deterministic forecast that we verify every day, the headline scores, and you can see the GraphCast. There are 2 versions of it. One is running with a slightly different configuration than the other one, but both have outperformed GFS, not as good as ECMWF, but still a significant improvement in the last 90 days, as you can see in this graph. And the next one is a tropical cyclone forecasts. We have run TC tracker on these forecast fields thanks to the Hurricane team for producing these graphs. The TGFS is the GraphCast test and has a significant improvement over operational GFS for Atlantic tracks. Not so much in the Western Pacific, but the early results are really encouraging and potentially augment what we can provide with our global ensemble forecast system and the deterministic GFS. So with that, I will stop and move on to the next talk. The next one will be from TWD. Oh, sorry, this is from NRL. Jim Doyle. Jim, can you hear us?
Yes, so can you hear me okay?
Yep.
Okay, I think we're going to drive the slides, or you guys are going to drive the slides, so we can start.
Yeah, go ahead.
First, yeah, I don't see the slides yet.
Yep, they're coming.
I'd just like to say first, thanks very much for including us in the schedule. John Moskaitis and I will do a tag team, and the outline is shown here. First of all, I'd like to thank the COEMS TC team also, not only John, but as well as Kevin Prince and Yi Jin, and thank our sponsors at ONR. Begin with COEMS TC background, talk about the deterministic forecast performance, a few highlights from 2024, then John will take over talking about the COEMS TC ensemble, and then some summary and future plans. Next, please. Okay, COEMS TC, you're probably well familiar with it. It's a version of the COEMS mesoscale model. It has specialized physics. We're still at 4-kilometer resolution. We'll talk more about that in a moment. Coupled to NCOM, and when it's not coupled to NCOM, we have a SST parameterization that works pretty well too. Next, please. Okay, the current real-time capabilities, there's two flavors of COEMS TC. The COTC is the NavGem-based system, and CTCX is the GFS-based system, which is better performing. And for the deterministic, FINMOC runs all areas around the globe for COTC, and CTCX runs the Westpac, Indian Ocean, Southern Hemisphere storms every 6 hours. We also have an ensemble that's running operationally at FINMOC, 11 members, up to 2 storms every 6 hours, with JT prioritizing those. At NRL, we run CTCX for all storms in an experimental mode, but we also produce forecasts for the Atlantic, Central, and Eastern Pacific, and those are provided to NHC and CP8C. We also run an experimental 21-member ensemble twice daily. It's kind of depending. We prioritize the Westpac and Atlantic, and it's not run on dedicated nodes, so we have some latency issues. Next, please. So we're highlighting the 2024 Atlantic skill performance with CTCX. I'd just like to note that we had some issues early in the season of getting the forecast to NHC. Although they were running, and they're running on a new supercomputer, we had a lot of difficulties getting the new Navy supercomputer talking with the NHC server. So thanks very much to the folks at NHC that helped us, as well as NCO and the Navy DSRC. So it took us quite some time to iron that out. So we missed some early forecasts to NHC. So this is our full sample, and you can see a track error on the left, and you can see in blue CTCX is very competitive with the other models and actually on par with GFS, especially in the western part of the basin. It did very well in the Atlantic. On the right is the intensity, and CTCX really struggled with the RIs at Beryl and Milton. There's a lot of cases for those, and those are relatively small storms, and it led to a low bias and relatively poor accuracy. Next, please. On a highlight note, if we look at storms from 2022 to 24, were CONUS hurricane landfall cases. A number of these cases from Ian all the way through Milton. The sample includes a fairly large sample, and you can see the track forecast for CTCX were really excellent for these cases. Although, you know, the sample we're kind of cherry picking here, but this is based on kind of the big headline landfalling storms that occurred in that period. So we want to understand this a bit better and try to characterize the track error performance as a function of the initial position to get a better understanding. Next, please. Take a look at the East Pack and Central Pack combined. CTCX is in the mix. Track error similar to GFS and other GFS-based regional models. And the intensity overall underpredicted the intensity for Gilma and Christie in the East Pack, but did very well on 1C. But overall, it still has a bit of a weak bias. Next, please. Now take a closer look at Milton. These are the COEMS TC forecasts shown in the blue lines, the forecast tracks, and the black lines are the black line is the observed track, and the pink dots show the forecast initial positions. The early forecasts, and you can see the zoom in the part on the right near the landfall. And so the early forecast made landfall too far south, but the later forecasts were really consistent just north of the observed landfall position. Overall, CTCX did very well on the timing of the landfall and had the best accuracy forecast for track amongst the GFS family of models. Next, please. If we look at the highlights here for intensity, not so good. The Milton, of course, had the extreme RI to Cat4 over a really short period of time, had a really small inner core, which was not really captured by CTCX. The 4-kilometer resolution is not sufficient to be able to resolve that. Would like to go to higher resolution. Our operational partner, FinMock, doesn't have the resources for that right now, but we're hoping in the near future to start to work on that and hopefully transition that in the next couple of years. Nonetheless, all the forecasts, but 3 of them produced a major hurricane just before landfall. So it did really well in terms of forecasting a strong storm making landfall. Next, please. The same kind of highlights here for Helene now. And so you could see the track forecast on the left and the zoom at landfall time on the right. The green dot showing the observed TC position at time of landfall, closest to the landfall time. This is a 6-hour position. Forecast tended to be somewhat too far west with the landfall location, but similar to Milton, the timing of the landfall was very well forecasted. So overall, track forecasts were quite good. Next, please. Intensity-wise, CTCX did very well to indicate rapid intensification. Many of the forecasts had the right idea about the right intensification rate, capturing close to the peak intensity. It certainly predicted a major hurricane peak intensity just prior to landfall. They had a larger inner core than Milton, and so CTCX was able to handle that and simulate it much more realistically. Next, please. And I think John will take over from here.
Okay, thanks, Jim. So yeah, I'll talk about the upcoming upgrade to the 2024 COEMS TC Ensemble. So that will be delivered to FinMock, maybe even this week, but sometime during first quarter of 2025. So just a little bit of background. So the ensemble right now runs as a 10-member ensemble. It uses the same grid configuration as the deterministic, and for the most part, the same physics. So here's what it looks like for 10 members for a storm from the Western Pacific from last year, Super Typhoon Mawar. So just to orient you, on the right, the best track is the dashed black line, so it goes right over the north side of Guam. And the ensemble members are the light dashed, or the light gray lines. The ensemble mean is the thicker gray line. So that's with 10 members. So can you go to the next one? So we're advocating to go for more members this year. So this is what the same forecast looks like with 15 members. So it's kind of fleshing out the distribution a bit. And it's also moving the ensemble mean a little closer to the best track. If you go to the last one, or the next slide. So again, this is the same forecast, just using 20 members for this particular case. So now we've fleshed out the distribution. It's a little bit, I think, more clear that there's a threat to Guam from this case with 3 or 4 members coming near the island. And it's also improved the ensemble mean a bit. It kind of walked that thick gray line a little closer to the best track. So this year we're advocating for 15 to 20 perturbed ensemble members instead of 10 for the operational forecast. It'll depend on FinMock resources to some degree, but we think this looks like a strong candidate. And if you go to the next slide, we've done some analysis of this. I'll just share one quick result. So the ensemble mean error statistics for track and intensity are both improved using 21 members versus 11 members. So the graph on the right shows the percent improvement in track in the dashed blue line. So, not huge improvements. It's between 0 and 2%, but it's positive for the 21 member ensemble versus the 11 member. And for the ensemble mean intensity, you're getting somewhat larger improvements using more members, around maybe 2% overall in terms of ensemble mean intensity, mean absolute error. Okay, next one. So the other major part of the upcoming transition is that we've developed a new suite of graphical forecast products that are based on the ensemble model fields rather than the ATCF text forecast file. So I'll just show a few examples here. So this one is, this particular plot shows the storm environment from the 12-kilometer CONUPS-DC grid, which is the larger of the two storm following grids. So the case here is Hurricane Helene from the September 25th, 12 the initial time, 36-hour forecast when it's getting close to landfall. So this graphic shows the 600 to 850 HPA relative humidity and the color shading. You can see the kind of dry air approaching from the southwest as the storm starts interacting with the trough in this case. The barbs show the 200 to 850 millibar or HPA steering flow. So, right over the center of the TC, it's 15, I think it's 15 meters per second. The storm was really moving fast as it came into landfall. And then finally, the blue contours show the 200 to 850 hectopascal vertical wind shear, which is picking up on as it made landfall. And sort of these, the wind shear and steering flow calculations are done by doing a vorticity inversion technique that removes the signature of the TC. All right, so let's go to the next one. So I think Levi from JTWC showed an example of this plot yesterday in his talk. This is our kind of vortex characteristics plot using the 4-kilometer innermost grid. Again, this is the Helene example from 12 the initial time, 36-hour forecast near landfall. So the color shading is the composite, the ensemble mean composite reflectivity. And then there's the ensemble mean 10-meter wind speeds and ensemble mean sea level pressure as well. So and then the magenta line shows the region, or the stippled region, encloses the composite reflectivity standard deviation greater than 10 dBz. So it shows some aspects of both the ensemble mean and the variability. And in this case, you can see the asymmetry of the precipitation field with most of precipitation to the north. And the ensemble is pretty confident that this asymmetry, at least outside the inner core, was going to be the case. As you can see, less uncertainty in the dBs, in the composite reflectivity to the north of the storm. Okay, next one. So one more example of this isn't everything, but one more example of the new graphics suite is wind speed exceedance probabilities. So this plot again shows Helene, this time for the 24 to 48 hour forecast window. The colors show the probability that the wind speed exceeds 34 knots during that time interval. And the black lines are all the different forecast tracks valid during the 24 to 48 hour time window. So Helene was a big storm, and the ensemble basically gave, almost 100% probability for 34 knot winds exceeding the 34 knot threshold between the forecast track and the west coast of Florida. Okay, let's go to the next slide. All right, so I'll summarize things here and give a little information about our future plans. So in terms of CTCX deterministic forecast performance that Jim talked about earlier, so the model continues to be a high-performing track forecast model in the Atlantic, especially for recent CONUS landfalling hurricane cases. The model did struggle with a number of RI cases in the Atlantic and East Pac in 2024, Beryl, Milton, and Christie in particular, which motivates finer grid spacing, I think, in the future, as our kind of computing capability of our operational partner allows for that. So for 2025, as I mentioned, we're going to transition the V2024 COMEP-CC ensemble that will be delivered to FINMOC soon and will be available for operational use in the 2025 Northern Hemisphere tropical cyclone season. And we also plan to deliver version 2025 deterministic COMEP-CC in the third quarter of FY25, again in time for the next hurricane season, with some improved physics. We're especially looking at microphysics, perhaps upgrading to the Morrison scheme, and some updated tracker and post-processing items. And in terms of kind of longer term future directions, so deterministic, we want to go to finer grid spacing in the horizontal and vertical, and also optimize the physics in the context of this new grid spacing. And then ensemble, we're looking at improved perturbation methodologies for better calibration of intensity and certainty. Right now in the ensemble, the intensity spread is a good bit lower than the kind of the average error of the ensemble mean intensity. So we want to better calibrate the ensemble to bring that into line. And kind of in the farther future, we imagine that the ensemble will sort of take over for the deterministic, and they'll just be the deterministic will just be the control of the ensemble member, similar to what ECMWF does now with their ensemble. So anyway, that's all we have, and I guess we'll perhaps take questions during the discussion period. Thank you.
Thank you, Jim and John. We'll move to the last talk of the session, but not the least, from Michael Denard, DWD.
Hi to Miami. This is Michael. Can you drive the slides for me?
Yes, we will be doing that. Give us a second.
Thanks.
All right, take it away.
Thank you very much. Yeah, this is I will give you an overview of what we had done at DWD last year, and I try to give you an impression of where we're going, since the machine learning stuff has overruled most of us. Surprisingly, we have to react on this situation, and so in Europe there's a ongoing initiative on developing structures for machine learning development, and I will give you an introduction to this as well. The icon model, I've summarized on this slide the major changes that had been done last year, and I just want to make a focus on the icon adaptive parameter tuning that was introduced by Günther Zengel in 2023, and he's continuously developing or improving this system, and I like it very much because it is a very nice idea of how to tune a model according to the information that you have at initial time. So what you have is the data assimilation increments, and of course you want to assimilate your variables or observations that you have into the model, and but this is can be difficult due to biases, and these bias corrections enable you to assimilate more observations, like 2-meter temperatures, for example, but also near surface winds as well, which gives you possibly improved wind forecasts, especially in tropical cyclones. And the nice thing about this idea is that whenever you start a forecast, you have started with a slightly different model, because you have adapted the parameters in the model which are sensitive to the biases in the observations. That's one point, and the second point on this slide is changes we have made in the ensemble system, because we have reduced the SST perturbations. Since we are running a global LETKF system, we take the background error covariances from the ensemble, and ensemble spread is very crucial in running the data assimilation system. So, it's not only about if the ensemble background error covariances go to 0 because the ensemble spread decreases, or we have not enough ensemble spread, the model rejects the observations, and that's not what we want to. So that's why SST perturbation have been introduced into this system. And but when you do a forecast, it can be shown that these SST perturbations were too large to bring out good forecasts. And yeah, it's now possible that we have a reduction of SST perturbations because Günther, he added additional perturbations instead to the entrainment in convection updrafts and the convective adjustment timescales. And this is a very important thing because these parameters affect the intensity of cyclones. And yeah, it is shown also by Linus Magnusson that these perturbations in their parameter physics-based
Did we lose Michael?
Yeah. Ask him. Can you hear?
Michael, can you hear us?
You just disappeared.
He's not on.
Yeah, he's not even on.
Well, while we are waiting for him to come back, we can.
Okay, excuse me, I'm back.
Oh, great, great.
I'm sorry, I lost my connection. My computer went down. I don't know why exactly this happened, but I can go on now if this is okay for you.
Yeah, please go ahead.
Okay. Okay, now on this slide, summarize the data assimilation changes that we had. And if you want to have a closer look at it, I added also the link where you can find it on the DWE web pages. And please, if you have any questions to these changes, ask the guys which are noted down there on, here on this slide. Next slide, please. The most important thing that happened last year was that we introduced a new forecast system. This is called the ICON ART, Aerosol and Reactive Trace Gases Ensemble. We're running now a 10-member ensemble plus a deterministic system, a system run for the prognostic treatment of reactive trace gases. So this is mostly due to the solar radiation stuff that affects the renewable energy industry. If you have any questions to this, please contact Linda. She's down that with her email. Next slide, please. Okay, so now my main topic is the machine learning structure in Europe. We are heavily contributing to this machine learning structure. It is led by the UMedNet organization, and it's called EAI program. And as you see here in green on the left, is the structure is very, very widespread. It includes all any possible applications of machine learning. One part of this structure is the ECMWF pilot project for machine learning, which I will talk about on the next slides and give you an overview exactly on this to have a focus on what how we develop machine learning in the context of NWP systems. Next slide, please. Right. So the main contribution that we have for this pilot machine learning project is the ICON model. This is a machine learning model that is built on the ICON grid. Because the ICON grid is very similar to what graphical neural networks are doing. And we try to keep the machine learning model as close as possible to the numerical weather prediction model. For many reasons. First of all, for having a direct comparison, possibly of direct comparison. We can also try to explain the structures that are established in the machine learning model. And also, we can possibly or hopefully improve both, not only the machine learning, but also possibly the NWP system, because we see that NWP and machine learning systems have different properties because they are of different nature, but they forecast the same problem. And so it's very interesting to see if we can learn something from the differences. To be as close as possible to the ICON modeling system, we train the neural network also with ICON reanalysis, with our own reanalysis, which is under development, and it is called the DREAM reanalysis. So it is an ensemble of 20 members with hourly reforecasts. Next slide, please. Data assimilation is also a contribution to the machine learning pilot project, where we did a simple step forward when you just replace the cost functions from the neural network. Normally, you just compare directly the output and the verification, but you also can try to learn the data assimilation cost function, which gives you an idea of what the mismatch of the output of the neural network is compared to not only to the background forecast or the forecast of your model or the reanalysis, but also directly, in this case, to the observations. So it gives you a possibility to put in observational information into the learning process or training process of the neural network. So you see some examples here. It is in a very early stage of development as well. Next slide, please. Ensemble systems. Of course, we also want to generate ensemble systems from machine learning models. So the question is how to do it best. It's an open question up to now. And our approach here is very similar to what generic machine learning models are doing. We have a denoising step from a random perturbation vector, but we are not trying to simulate a generic ensemble system, but we add some old stuff here, which is the singular vector algorithm, because I did a picture on the left. When you look at it, you see it is very similar to a denoising step of a generic machine learning model. However, we have the yellow boxes where we do some matrix multiplications and some additional stuff, which is involved in the singular vector calculation. And it turned out that we just need one denoising step of, let's say, n steps to generate an n member ensemble forecast. And this works well in a way that we can generate growing perturbations. This is the middle figure on that slide, which are the blue lines. These are the unperturbed forecasts. And what I showed here is the vertically integrated perturbation energy. And the black line in this middle graph is when you start just from random perturbations. So in the beginning, random perturbations will be damped in the machine learning model, and after 2 or 3 days, as it's very similar to NWP systems, the error, the perturbation grows also. The right figure shows you that these perturbation structures are related to the dynamical flow of the atmosphere in the model. So what we get from the singular vector calculations, or from the combination of a singular vector calculation with a denoising step in a machine learning model, is flow-dependent initial perturbations. Next slide, please. Okay, I'm trying hard to keep our cyclone tracking system at DWD alive. I think it's very important to have such a system for evaluation of cyclones, tropical cyclones, but also for us, medicanes and other cyclones, extratropical things, because I think it's very important if we want to tackle the limits of predictability. It's really, really important to see how the models are able to forecast these cyclones, and we also want to include machine learning models here. Next slide and last slide. This is some example from this tracking system. What you see here is the upper plot is the icon model, the lower plot from the IFS, and plotted is specific strike probability. The strike probability is tuned such that the red color turns into yellow, green, and blue. So goes to lower probabilities only if there are missing members, or there are members that do not forecast the cyclone anymore. So, and you get here an impression of where we have cyclonic activity, and we have different types of cyclones all over the globe, and it is nice to compare it to ECMWF, where we see that ECMWF has some better or less spread in their cyclone forecast than we have in the icon model. So this is the basic of further evaluation. Thank you very much, and I leave you with this slide. Thank you.
Thank you, Michael. So that wraps up the presentations part of it. Let's get into the discussions. Any comments, questions to any speakers? Mike.
This is Mark DeMaria from Sierra. A lot of interesting presentations in that, but one thing I saw from all 4 of the global modeling centers is that it looks like they're making a pretty big commitment to the AIWP, and the European Center and Michael's talk at the end here. It looks like they're pretty committed to basically developing their own systems and maintaining it and using that maybe for ensembles. So my question is more for Vijay and for Julian. In your presentation, Vijay, it looked like you're actually not just using GraphCast, but you're retraining GraphCast on GFS analyses, and then that's going to possibly, you got a bullet for your ensemble system. And for Julian, it sounded like he was running Pango Weather, but I wasn't sure whether UK Met Office is just going to try to download the the open source models and just run it, or whether you're committed to actually doing in-house development of your own and maintaining your own AIWP system. So it's a question for Julie, I guess. Vijay, you're right here, and then also Julian, curious about your plans as well.
Yeah, I'll let Julian talk first, and then I'll ask Daryl to respond for EMC. Julian?
Yeah, thanks, Mark. The Pangu weather was an initial kind of delve into the AI world, if you like, to see what we could do in quickly in real time. But there is a whole team being assembled to look at kind of more in-house developments. We've got something called FastNet being developed, and there's other systems as well. I have to admit, we're not as far advanced as the likes of ECMWF down this track, but yeah, the Penguin weather was just the kind of initial look at the whole idea and what it might produce for us. But we're certainly spinning up a much broader based team to look more into the development of AI models in the future.
Thanks for the great question. And it's something we've been grappling with quite a bit across NOAA. We have a cross-line office team that's been spearheading and trying to accelerate our efforts here. We've actually been working with political leadership to get a roadmap for NOAA done ASAP before an administration change. I think we're going to have that done in response to an SAB set of recommendations, I think next month. Right now, the plan is likely to connect to Anemoy and see what we can co-develop along with partners at ECMWF and elsewhere. Very likely doing derivatives of GraphCast. So AIFS is sort of a derivative of GraphCast using graph neural nets. Now starting to play with diffusion models and under things like that under the hood. We're very likely going to do something similar. Details still to be worked out, but we're building the roadmap and defining the partnership so we have a consolidated effort moving forward.
Thank you, Daryl. Thank you, Julian. Any other questions, comments for any of the speakers?
Hello. It's a very generic question, not from anyone specific, but like GraphCast and such models are based on basically an existing mesh based on the neural net on a graph. I know there are recent developments in working on function spaces, and it's called like neural operators. I was wondering if anyone has explored or have seen any weather model using neural operators where you don't have any resolution restriction. You can basically map it however you want after you have the model trained. Thanks. This is Suresh Mani from UFS Survey.
Okay, Lenas, you want to take that?
Well, a bit complicated question, but another stride on this machine learning model is learning directly from observations, which then might create a whole different kind of grid on non-grid. So it will be interesting to follow it in the future to see if the concept of grid and resolution would disappear in a machine learning world, or whether we're still going to use some sort of mesh in the future.
Hi, I'm Ferran Alet from Google DeepMind. So one thing I'd like to add is that graph neural networks are not necessarily incompatible with having kind of arbitrary resolution on the input space. You can kind of use them as a computational substrate where you kind of take observations on continuous positions, and then you let them inform the mesh, and then you propagate on a finite element method like mesh, and then you predict back on kind of infinite resolution. But there are other alternative approaches, I guess, from NVIDIA, Fourier neural operators that are kind of an alternative to graph neural networks or transformer-based architectures.
It's a great point. Thank you. Stan.
Stan Goldenberg, HRD. Going back to the very first talk, when you're showing the resolution of the structure of the hurricane on GFS versus regional, it would help to reiterate the resolution difference. I mean, you're talking about vast difference in resolution, so I would expect it to be able to pick up those things. And by the way, when you're mentioning up the GFS spinning something out of nothing, I remember when I first got started under Gopal with this stuff, and I was looking at GFS, I was amazed just as a novice looking at these models, how out of nothing the GFS would realize, oh, there should be a vortex there, and spin it up in a not too long period of time, even though there was nothing initialized. So thank you.
Yeah, that's a great point, Stan. I think resolution matters for structure. It is, I think, 13-kilometer GFS compared to 1.5-kilometer HAFS. Yeah.
It's a question. I think Julian showed this. He was showing AI models versus deterministic models. In one of the forecasts, if I remember, it's Julian, one of the forecasts, all of them missed the real tracks, basically. It was so biased. So why is this happening, basically? Is it because, I mean, are we trying to follow everything from the numerical models and this is just going to give an ensemble? Trying to understand the science behind it. How could we miss totally track prediction? None of the models got it, neither did AI get it. Any comments? Is it from Julian, I think, right? That's what he was showing.
I don't think it was in my presentation.
Yeah, I think it was in mine.
Linus, sorry, from ECN. Yeah. Sorry. Yeah, go ahead, Linus.
What we have to remember is that also the AI models are initialized from the same initial condition, so the NWP analysis. So if the tracker error is coming out from an initial condition error, then the machine learning model should suffer from it in a similar way.
So it's an initial condition problem. Once again, we are facing even with the AI models. That's what I wanted to understand. Okay.
Yeah, that's probably the main cause of the same behavior from AI models. Maybe slightly better, but they cannot eliminate all the errors due to initial conditions. We have a question online. Dave, do you want to speak up?
Oh, hi. Can you hear me?
Yep.
Oh, great. Thanks. I was just wondering with the talk of AI and, more AI models being tested and evolved, how important is it to maintain the model physics development and ocean atmosphere coupling improvements? I fear that if AI takes on more of a focus, it might lead decision makers to think that you don't need to keep up the foundational modeling physics and things like that. Thanks.
Who wants to take it? Linus, Julian, Michael?
I
Yeah, go ahead, Linus.
Go ahead, Linus.
Yeah, at least currently the AI models are trained on a reanalysis, and if the reanalysis is going to need a physical model in the future, then one still need to do the development of the model physics and coupling to improve the reanalysis. So that's one of the aspects I see. Go on, Michael.
Yeah, Julian, you want to respond?
Yeah, I was going to say the same as Linus, really, and particularly since I pointed out in my presentation that, for example, with tropical cycling intensity, the models which are relying on things like the ERA5, relatively low resolution reanalysis, are doing very poorly for intensity. So I think there's even more focus now, as we've just been saying, on initial conditions, on good high quality, high resolution analyses, certainly for models, AI models, which are very dependent and using, being trained on that kind of data.
This is Daryl Kleiss from EMC. Also, I don't think it's a question of either or, it's and. And in fact, there's a lot of work we can do to accelerate some of the sore spots we have in physics and DA by leveraging AI. So there's hyper focus on trying to solve the big problem and building emulators. There's a lot of work in between that we could use to leverage technology to make breakthroughs in things we've been stuck on for decades. Thinking of some of the big physics problems, thinking of some of the big DA problems. So I think we need to invest in and keep doing both.
Well said.
Thanks for that. I just Jim, go ahead. If Jim wanted to say.
Frank Marks, no HRD. So if analysis is the critical piece here for training AI, is there any thought about doing a high resolution hurricane reanalysis to inform? I saw one of the talks they're doing multidimensional model inputs. I think it was Michael Denhart. And so is there any thought about doing reanalysis of the hurricane models like HAFS or any of the different models, H1?
Yeah, that's a great question, Frank. I think we put PCS for developing the hurricane reanalysis capability. Even the global reanalysis is far away from getting accomplished. So I think this is something that we need to reiterate, like what Daryl and Linus were mentioning. We need high resolution reanalysis. We need a better physical model too. So it is an and proposition rather than or. I want to ask one last question to the forecasters, how they perceive these AI models from their use perspective.
Yeah, I'll just kind of make a note here. So I've seen kind of the strides that a lot of the models, the AI models have made for tropical cyclone track forecasting, seeing significant improvements on track errors, showing even in these larger, mean statistics. But I think one of the deficiencies that we're still seeing in AI models is intensity forecasting, where there are significant errors that are well beyond what our current regular sort of coupled atmospheric, using kind of the traditional NWP framework seems to be doing still a much better job with intensity TC forecasting versus these AI models. And so that's something I think we need to work on next for this avenue.
Yeah, and I just add real quick to that, again, it matters about structure. And I don't think those models are going to get structure anytime in the near future. So we still need the higher resolution models to provide the structure forecast for hazard footprint things.
No, I have a different question. I know AI is attracting a lot of attention, obviously, here, but I just want to go back to earlier presentation HAF. So you guys show there some of the issues with initialization, the consistency from run to run, but I'm not quite sure I saw on the slide in terms of plan upgrades for the next year or two, if whatever comes out of that, looking into those issues, if it will be put into the model, right? What I'm thinking is, yeah, there is a W cost transition coming. There is the moratorium W cost. It's a year that you cannot do anything. And then there is the issue of, obviously, here we have another year. We thought we were going to get rid of H4, H1 last year. Well, as data is showing us, no, not quite yet. Well, if those issues are not addressed in the next year or two, now you begin to run into an interesting conundrum here. When do we really phase out H4, H1 at the detriment of the consensus and the guidance overall, if these issues are not addressed on time before that transition gets here? In my mind, just asking all these questions, and I would like the group to address that.
Right, Pablo. We are also asking the same questions from the model development point of view, when we can switch off the H4, H1 and improve the HAFS that meets or exceeds the standards that we set up. More will be coming in the near future in terms of finalizing those plans. But anything that we do in real time and advancing the HAFS will lead us towards making that decision when to retire the H4 and H1. Apart from looking at those timelines that you mentioned, it's important that we address those known issues and then discuss with NHC how to move forward.
I'm going to have to cut everybody off because we're already eating into our break quite a bit. So we will be back at 10:45 for the next session. Sorry. Thank you.
Thanks, everybody, again.